From coding agents that learn what to remember across wildly different tasks, to video models that can generate richly synchronized audiovisual worlds, to spatial AI that teaches itself through deterministic geometry, this episode dives into 3 papers pushing the boundaries of what intelligent systems can do. We'll explore how abstraction boosts transfer, how multimodal generation is becoming more controllable and expressive, and how grounded self-evolution may unlock stronger 3D reasoning. If you're curious where AI is headed next, this one's for you. Let's explore the first paper, Memory Transfer Learning, how memories are transferred across domains in coding agents. Memory transfer learning studies whether coding agent memories can transfer across heterogeneous programming domains instead of staying confined to a single benchmark. The authors build a 2-stage agent around GPT-5, Mini, Sway agent, and embedding-based retrieval, then generate 4 memory formats from prior trajectories: trajectory, workflow, summary, and insight, evaluated on 6 benchmarks: Live Code Bench v6, Aider Polyglot, SWE Bench Verified, Terminal Bench 2, Replication Bench, and MLGym Bench cross-domain memory improves average, pass at 3 by 3.7% over zero shot, with insight performing best and reaching gains of up to 8.3% on individual benchmarks. Compared with self-evolving baselines, memory transfer learning outperforms Reasoning Bank and Agent KB by 2.9% and 1.7% on average, respectively, despite using only 431 memories versus Agent KB's 5,899. The central mechanism is not task-specific code reuse, but meta-knowledge transfer, validation routines, inspection-first workflows, environment adaptation, interface compliance, and anti-pattern avoidance. The paper shows that abstraction is the main predictor of transferability, with higher-level memory formats mixing more across domains in t-SNE, higher LISI, and lower domain specificity, while low-level trajectory memories often cause negative transfer through brittle anchoring and wrong command imitation. Task-agnostic insight memories outperform task-specific ones even within the same format, and performance scales with both memory pool size and number of source domains. Cross-model transfer also works, improving GPT, 5, Mini, DeepSeek, V, 3, 2, and Qwen 3. Coder targets, though self-generated memories remain strongest. Let's explore the second paper, Seedance 2 Advancing Video Generation for World Complexity. Seedance 2 is ByteDance Seed's native multimodal audio-video generation model, extending Seedance 1, 0 over 1, 5 from synchronized audio-video synthesis to unified text, image, audio, and video conditioning with integrated reference, editing, and continuation controls. It generates 4 15-second clips at 480p, 720p, and supports up to 3 video clips, 9 images, and 3 audio clips as references. On the new Seed Video Bench 2 benchmark, built with media industry experts and split into objective and blind subjective tracks, Seedance 2 ranks first across T2V, I2V, and R2V. In T2V, it raises the overall score from Seedance 1.5 by 0.86 points on average, with motion quality improving from 2.39 to 3.75, and audio-visual sync from 2.91 to 3.75. Usability reaches 97.55% on motion and exceeds 83% on every dimension, while satisfaction surpasses 51% on all 6 metrics. It ranks first on 29 over 30 motion subcategories, peaking at 4.43 on multi-entity feature matching and 4.21 on editing rhythm. Audio is a major novelty: dual-channel binaural output, multi-track layering, and synchronized dialogue. Background, FX yield, first-place scores on all 17 audio categories, including English 4.17, Chinese opera 3.75, and voice action interaction 4. In I2V, Seedance 2 again leads all 6 dimensions, reaching 3.7 on audio prompt following and 3.61 on audio quality, expression, with 87.05% usability on motion and 97.42% on audio quality. It shows the strongest gains on complex instruction following, especially compound multi-instruction tasks, MQ4, VPF 3.75, and on complex motion, including combat visual effects, MQ 3.63, and micro expression, emotion, VPF 4. In R2V, it supports 20/22 task modalities, uniquely covering visual effects, creative reference and continuation, extension, and liaison editing consistency. 3.54, reference alignment 3.03, and motion quality 3.24. The main residual weakness is video extension, where VEO 3.1 slightly outperforms it on task following. Let's explore the third paper, Spatial Evo Self-Evolving Spatial Intelligence via Deterministic Geometric Environments. Spatial Evo introduces a physically grounded self-evolution loop for 3D spatial reasoning by replacing consensus-derived pseudo-labels with deterministic supervision computed directly from scene geometry. Its deterministic geometric environment, DGE, formalizes 16 task categories spanning scene level, single image, and image pair reasoning, and programmatically verifies question legality before synthesizing exact ground truth from ScanNet, ScanNet++, and ARKit scenes point clouds plus calibrated camera poses. A single Qwen2 5VL policy is trained with GRPO in dual roles. As questioner, it emits grounded spatial questions under strict validity constraints. As solver, it answers or explains invalidation reasons using DGE outputs. A lightweight, task-adaptive scheduler reweights sampling by historical accuracy, creating an endogenous curriculum that concentrates training on weak categories without manual design. Across 9 benchmarks, Spatial Evo attains the best mean performance at both 3B and 7B scales, reaching 51.1 and 54.7 average score, respectively, while preserving general visual capability on MMStar and real-world QA. On VSI Bench, it reaches 39, 2/46, 1, and on MSpatial, 61, 2/66, 0 for 3B, 7B, consistently outperforming static dataset baselines such as Spatial Ladder, Spacer, and Spatial SSRL. Ablations show that removing deterministic physical grounding causes the largest collapse, dropping the 7B average from 54.7 to 49.6 and VSI Bench from 46.1 to 18.8, confirming that model vote pseudo-labels inject harmful bias. The paper's main novelty is that 3D spatial supervision is treated as an executable property of the environment rather than a learned proxy, enabling zero-noise online curriculum, learning from unlabeled indoor scenes. That's a wrap on today's AI paper highlights. Thanks for watching.